Hi to everyone, my name is Matthias, I'm the technical support engineer for Trimber's eCognition software, and this is another eCognition Deconstructed video. Today we're gonna again look at pixel-based object resizing. This is the second video, so if you haven't watched the first one, please go ahead and do so, and then return to this video. As you remember, the pixel-based object resizing can be used to reshape your objects, and actually the candidate surface tension is a special setting that you can use to grow and shrink your objects. And what does surface tension mean? So I'm going to read this from the reference book. The surface tension uses the relative area of classified objects region feature of pixels of a given class to optimize the image object shape while resizing. Within a cube of given size around the current candidate pixel, the ratio of relative area of seed pixels to all pixels inside the box is calculated. So I admit that this sounds complicated, and actually it also is a bit complicated, but after this video I think you're gonna understand what it's doing, and then you can go ahead and use it, and it's gonna help you out a lot. So these are the settings here on this list that you can use for candidate surface tension: the reference operation value, box size in X and Y, and box size in Z. And let's go from top to bottom. Reference is either object or class, and I try to illustrate this on this figure on the right hand side. If you choose object as reference, then the pixels of current image object are considered for relative area measurement, and if you choose class, pixels of a given class are considered for relative area measurement. So if two objects of the same class fall within your bounding box, your box size, and you choose class, both are considered in the relative area measurement, and if you choose object, only the object, the current active object, is considered, and not the neighboring that might overlap your bounding box. Okay, you can choose these different operations that are listed here, then a value between 0 and 1 for the relative area measurement, which equals to 0% and 100%. Then you can define the box size in X and Y, so 5 times 5 for example, so if a filter of 5 times 5 pixels, so 25 pixels, or 20 times 20, 400 times 400, whatever you want. And the last one is the set direction of your box, but we're not going to touch this in this video. Let's have a look at an example. So if you choose growing and set the surface tension to smaller or equal than 0.5, and a box size of 5, so we have 25 pixels. What you see here is in gray, that's an object classification, and we have this box in blue highlighted the active pixel. Now this box runs over your whole image like a moving window and calculates for each active pixel the percentage of pixels that are belonging to that class within that bounding box. And then it evaluates if it's true or false, and if it's true, it executes the growing or shrinking or whatever you defined, and if it's false, it just moves on. And let's have a look at this first frame here. In this case, in this moving window, in this bounding box, we have 9 out of 25, and I believe now our condition is true, so this is less than 0.5%, so 50% of 25 pixels, right? Therefore, it's gonna grow. And then it moves on to the next pixel. Let's also discuss this briefly, because this one is false. So the area of, or number of pixels within that bounding box that are classified is larger than 50% and not smaller, so it's false. And then it just keeps on moving, it doesn't grow, it goes to the next pixel. And this is done for the whole image. And let's just look at this animation and see what would be the final result of this whole image object after we applied this algorithm. Here we are already, so all these bright gray pixel objects would be added to that object, applying this algorithm and these settings, and the object would look like this. Running the algorithm a second time, the object would grow again, and all these bright pixel objects would be added afterwards. Let's have a look after this theory part at a bit more meaningful settings, like growing larger or equal to 0.5. And this setting is actually very helpful to improve the shape of your objects, and you're gonna see why after this animation. So it's gonna do exactly the same than before, simply the condition is different, it's larger or equal to 0.5, and it runs over the whole object or your whole image and evaluates each pixel. And each time it's true, it's gonna add the pixels adjacent to the active pixel, the blue one. After one execution, your object would look like this, so these would be added and would look like this. And just to compare it, the red outline was before the execution. If you execute it a second time, the object would look like this. Here you see the evolution of the object, so it's growing actually. Using these settings, the side effect, a very nice side effect, is that you're closing these narrow gaps that you have. So the object is becoming more compact when setting growing to larger than 0.5. Now we're going to have a look at shrinking, and we're going to do the opposite. We're going to set it to smaller or equal to 0.5. This follows also exactly the same procedure as before, but instead of growing and adding pixels, it's shrinking, so it's removing pixels, indicated in yellow here. So each time it's true, it's going to remove that pixel. And a side effect of this one is that you're going to remove these small arms reaching out of your objects, so it's becoming more compact. So we're not closing these gaps, we're removing these tiny little arms that are reaching out of your object. And in combination afterwards, if you use it in combination, we're going to do this in eCognition in a second, you actually can create very nice compact objects and improve the outlines of your objects. Alright, let's go to eCognition and apply these algorithms. But first we're going to set up a project. I loaded a Sentinel-2 image here with agricultural areas. To create the objects, I calculate the NDVI and did the segmentation and also copied it to a second map. So we're going to apply our algorithms on map 2, and we're going to keep the main map for comparison reasons. And after the segmentation, it's going to look like this. So the goal is to get nice irrigation circles, so each circle should be a single object and should have a nice circular outline. But after this segmentation that I did, these objects are still connected. So let's think about an approach how to split them up. And actually, based on what you've learned in the previous video, you can do this. So what we're going to do is we're going to use a combination of shrinking and growing to actually split these objects into single objects. So first we shrink them so they're disconnected, and then grow them back into their original size. I already prepared a short section here within the rule set, which is actually exactly doing this. So it's called the shrink and grow strategy. So we shrink and grow, and this will separate our agricultural parcel classification. Let's execute this one. Now on top we have map 2, so we're working map 2, and on bottom you see the main map where we have our initial segmentation and classification for comparison. So you notice we split these objects up, and now we have nice single irrigation circles on top. You also see the number of agricultural parcels. On bottom is 600, and top we have more than 900, so we increase the number of these circles. Okay, now let's have a look at the surface tension stuff that I was talking about previously. So let's append a new process, look for pixel-based object resizing. We are interested in reshaping our green class, so the agricultural parcel class, and we have to set map to map 2 because we have 2 maps and we are working on map 2 now. Let's scroll down here in the algorithm parameters to the candidate surface tension. As reference, we're going to use object. You also could use class, but we're going to use object. And we're going to set exactly the same settings as we had in the demonstration before, so 0.5, and it's set to growing. Okay. Let's execute this one. So it did it once, and you might have noticed that something changed. So let's zoom into a special case. Here you see that already it grew into this unclassified area based on the surface tension settings. Let's increase the number of loops, of cycles to 30, and execute this one so it does it 30 times in a row. You're going to see that these areas are going to vanish compared to the initial segmentation. So we filled these gaps based on this growing and the surface tension settings. Let's simply copy and paste this algorithm. I'm just going to look for a nice area. Here we're going to see something changing when we use the shrinking approach and the surface tension settings that I showed previously. So let's just copy and paste this with Ctrl C and Ctrl V and change growing to shrinking. And we're going to put this new class into removed, so you're going to see what's happening, and we set the operation to small or equal to 0.5 and keep the number of cycles to 30 and just execute this. And you're going to notice that these outreaching arms, these small features, are going to disappear. So I've put them into this yellow class and they are removed from your classification. Again, on bottom you see the initial segmentation and on top the refined one. It's not perfect yet, but it's just for you to get the idea. So we split up the objects and then refined them and smoothened the outline. And I think it looks already more realistic, right? It always depends on what you want to achieve, but that was our initial goal, to get single objects and smooth the outline. Okay, so that's the end of the video. I believe this is fairly complicated, but just go ahead and try it yourself. Use different settings, different box sizes, and just play around with it and notice the differences. And please, if you have comments or questions, post them underneath the video, and have a good day.